Good evening, everyone. I welcome all of you in this talk organized by StatsUP. And today, as like you all perhaps seen in the poster, our goal is to learn a little bit about statistical analysis of networks. And specifically for how did I get the motivation for doing this is like, so I got this book and I was very eager to learn the contents and about this field of network analysis, but I was not getting any motivation to learn this. So this plan came up in my mind that it's better to share some knowledge with you and with that motivation learn a few things. So having said that, it is also a caution that I am not anyway an expert, not even a novice in this field. Just started learning this book and I got some interesting ideas, and based on that I prepared this slide. So yeah, I mean, you can ask me some questions, but I am like asking forgiveness beforehand if I can't answer anything. Okay, so having said that, this is the book by Polasic and Zardi. This is, I think, one of the user series published by Springer. This book comes under that series. Now, before starting, I just would like to mention a very mystical connection. So there is a famous verse in Bhagavad Gita, and it goes like Sri Bhagavan Uvacha, Urdhva Moolam Adhasakham Asatva Prahuravvayam Chandasi Yasya Pradani Yasta Veda Savedavid. So it means that there is an imperishable banyan tree that has its roots upwards and its branches down, and whose leaves are the Vedic hymns. One who knows this tree is the knower of the Vedas. So how is this relevant? Basically, later on we will study some structures like trees and forests. Maybe not in today's discussion, but somehow it shows that in this entire universe is some sense a network, a very complex network of defined attributes, and there are so many edges. We don't know how things operate here. So okay, with that spirit, we move on. And the first chapter. So basically, this slide is prepared exactly following the structure of the book. And I have summarized a few sections and subsections. So mostly the contents are taken from that book only. So what is network or why networks? So the phrase that we live in a connected world gives a lot of motivation for studying networks, like studying defined phenomena as graphs. It gives us very deep insights about many things. So for example, these online platforms, some social media platforms, the world wave, like the Internet of Things, IoT, and all these things, these are like huge networks, ever-growing networks, like the dynamic networks to be precise. Like some websites can be thought of as uh, vertices, and like how they are connected with different websites. Those connections can be thought of as edges. In Facebook or any social media, there is this friendship network where people are considered as nodes, and some edges in between them are considered as like friendship connections. And defined insights can be derived, right, from that. So formally, networks are actually modeled as graphs. In mathematical language terminology, these are like graphs. So the entire graph theory is essentially the background where this entire analysis operates. And we use network for general concept and network graph for its mathematical representation. But the origin is actually of this study of graph theory. I mean, it is also the origin of network analysis, right? So the graph theory, I think, as per the book says, it started, or the roots lie in this Euler's solution to a problem given by Königsberg. So this Königsberg's breach problem, I've just seeing the problem. It talks about like there are some landscapes and there are some rivers in between, a different, different paths of a river or its branches. So there are some bridges that connect those different landscapes, and it asks a question like, is there a path possible where you don't need to cross a bridge twice, or that kind of thing. So in order to solve that question, Euler converted that problem into a graph and edge kind of structure. So yeah, that kind of gave the motivation, even though he didn't define it in that way rigorously. It was sort of the origin of graph theory. And in network analysis, this data arrive in many diverse fields like biology, sociology, finance, social media is there, and like these dynamic networks, how political parties develop their relationship, how that changes the geopolitical situations can also be modeled using networks. So there's a vast amount of application and generalizations possible. So even though each field has like domain specific questions, but an unified approach can be given as, and it is like being given for the recent few years by many statisticians and data scientists, AI researchers. So like I would say in statistical literature, there are many uh, tests. So we initially, when we learn in the first few years of statistics, we study about this basic tests, right? Like the multivariate test or univariate test, this Fisher test, or all these kinds of testing for normality. But in high dimensional settings and in multivariate settings or non-parametric setup, many recent tests are proposed which are based on graphs. And there are many advantages of these methods. It has been seen. However, there are some disadvantages also. We will gradually discuss those things. Now, this book adopts a taxonomy of network analysis in these three broad classes. Like it starts with the descriptive analysis, where they discuss about summary statistics, visualizations. Then this talk about modeling and inference for network. So they talk about structures of network itself. So there are like different kinds of network generating mechanism like the ADOS, Shreni graphs, random graphs, and random networks. And after that, they model on network. So now we have a network, they kind of fit a model based on that framework or on that base. So this organization helps structure the methodology across domains. Think someone has some question?
Yes, Professor, with your permission, I'd like to ask a question.
Yeah, yeah, sure.
Yeah, so in the previous slide, you were
Hmm.
discussing those three reasons or three ways on which we can work on networks. So, is the
Right.
last one about using the data algorithm as a network based algorithm and then doing analysis? Is that what you were trying to say, or is it the second one, modeling and inference for
So
networks?
a modeling inference for networks is like you are giving the network a structure. So that means how the network will generate, it has an underlying structure. So in usually in ADOS Shreni graph, what happens? You have some edges, and sorry, you have some vertices. You have some vertices, and whether or not there will be an edge between any two vertices is a random variable. So in the simplest models, they assume that it is a Bernoulli with certain probabilities, right? So with probability P, an edge will form, and with 1 minus P, it will not form. So after all those, the randomness goes away, we get a realization of that random graph. And then we study its properties, like what is the number of triangles that will form in that graph. So like triangles, you can all understand like three kind of vertices will be connected. What is the number of clicks? And there are many such papers which like talk about those things. Like we don't know how many triangles will form or how many clicks will form in that network. So that is modeling the network. And what is modeling on networks? So now we have a network. The network is fixed, and we try to also, that is kind of a back tracing. So that is the same structure that we do in inference. We start with sampling distributions, right? We study if xi's follow normal, then what is the distribution of x bar divided by s, that standard deviation. It follows a t. So that is the theory. But in real life, what do you have? We have the data. So we go in the backward direction. So now we put the data and we see whether it follows a T, and that is judged by, this cutoffs. If it is lying within a decent position that it should lie, given it comes from a normal distribution, then we say that the null hypothesis is accepted. So modeling, and so the last point is like we have a network and we try to infer on that. So, and based on that, we conclude, oh, this network has this kind of properties. So does that answer the question, Pratik?
Yes, thanks.
Yeah. Okay. So having said that, okay, so the first chapter considers about this visualizing and characterizing networks. So this is subsection 1.2.1. So in types of network analysis, this descriptive methods only we will cover in today's session. So visualizing and characterizing these networks is very important. Why? So just like this Las Vegas law firm network, it has some lawyers and the vertices are like defined lawyers. The colors represent their office locations. Edges are like collaborative work relationships. So whether two lawyers collaborate, they are like working in a group or not. And like there are three female lawyers, so I think that is not denoted with anything. So if we see the graph now, you can see the structure. It has some square. So these are edges, right? These are edges which has some numbers in them, and the lines are, sorry, these are vertices and the lines are edges. I get confused with this edge and vertex anyway. So the structures represent, the shape represent the type of practice. So is it litigation or corporate? Okay, so defined sectors in law firms are there. That it is saying about this. And what does the color say? So the colors denote the office locations. So there is one outlier who has his office located somewhere else than entire bulk. So the whole point is that this one image contains so much of information, right? So much of information in the sense it talks about the different types of lawyers in different firms, also talk about their interdependence or collaboration. So a network can actually carry a lot of information, which, I mean, in this small page, you can't, I don't know about many such similar plots which can summarize that amount of information. So that is a great utilization of networks. So again, now there are some challenges with this visualization. Even though there are advantages, there are challenges. Again, some question. Yes, as another question. Yes, Ashan.
Yeah, am I audible?
Yeah, you are.
I wanted to ask that for the previous example, Las
Mhm,
Vegas law firm,
mhm,
as we can see, that there are different shapes and different colors corresponding to the different types of categorizations as to the types of lawyers and the based on the types of firms they're working and also I think the sex of the lawyers.
mhm,
So
mhm.
from this example, I can see that at most two types of categories were helping in distinguishing them with regards to the
Okay.
shape and the color. Now,
Mhm,
my next, I mean, the question that I'm trying to
mhm.
figure out from here is that what happens when we have more than two categories? Is there any sort of distinguishing visually
Yeah,
possible?
so if you have more categories, there are like two, three common tricks are there. So one is changing the shape, changing the color, and apart from that, like what is the possibility? I think like keeping them as clusters is also possible. So there are many such ways to represent.
Okay.
Yeah, but main is color and shape. That is main. Also another important thing is the vertex size. So I missed that. I think vertex size is years with palm. Yeah, so that information is also important. You will see some vertexes are larger than others. So this one is like a junior lawyer who has just started his work.
Experience then, I believe.
Yes. So these are three, I would say three main attributes: color, shape, and size, vertex size. So with these three things, you can actually incorporate a large amount of, I mean, defined possibilities, right?
Yes.
Yeah, so that is there. Okay, so
Thank you.
yeah, well, so again, there are some challenges as I was saying. So small networks are easy to visualize, but large scale networks have billions of nodes. Now, so there are ways to deal with that, but you can understand if we try to make such a plot for a Facebook data, friendship data, even for India, say, for India, I'm just leaving the question of plotting those things, like such a big country with so large a population. For small countries also, it is very or extremely difficult, and it will not give anything fruitful, right? So there are many methods to deal with those challenges, and similarly, like biological networks, gene-protein interaction networks are there. There are so many possible proteins, even in the smallest creatures like amoeba or yeast. I will show one data connected to the yeast interaction, I mean protein interaction data set. So we will see how we deal with those things. And yes, now this section also talks about like how different descriptive measures are used. So like clustering coefficient, assortivity coefficient. So clustering coefficient means like how likely it is a friend of a friend is also a friend. So they belong to a common cluster, right? So they have common ages. So I mean, essentially that is a path. You can move from one this vertex to another vertex through a connected path. So connectivity is an important aspect. Assortativity, it measures similarity between connected nodes based on an attribute. So are corporate lawyers more likely to collaborate with other corporate lawyers? So those kind of things. And you want to know the characteristics of a person for whom you have very little data, but they are connected with someone, and for that connection, they share some common attributes. So that also comes under this category. However, we will come to those things later. So these are like the chapter mm, descriptions that is given in the first chapter. So the roadmap of the book. And to understand network formation, the goal is to go beyond structure to understand how networks form. So this dynamics is also an important aspect for understanding any network. And there are like statistical models, like the most basic one is this KDOS random graph. And these things motivate the use of statistical models and their inference. So yes, like things I mentioned here, this Ederson graph, and it is used as null models or baselines. So theoretical properties are well known, but you can understand these are very simplistic for real life networks. Okay. So like that, the class 2 of statistical models is the fit to data to explain edge formation by a covariate. So like we have a data on which we fit a regression model. Similarly, there are graph data, and we try to fit this EGRMs are like exponential random graph models, latent space, stochastic block models. These are very popular, well-established models in graph theory, and gradually these things will come up. So similarly, there are network processes. I wrote these slides. Actually, I'm not going through them line by line. You all can understand. So these are like chapter synopsis. Dynamic process also is a very important field, and somehow the topic that I am also working on, change point analysis. Actually, one of the motivations for studying this topic is like I want to incorporate this in my own research. So these dynamic networks are like, you can think of them as networks which are evolving with time. Yes, that is essentially the case with any network, right? So at each timestamp, you get a snapshot of the network. And suddenly, suppose there is a sudden change in the network structure. So those time points are called change points. That is one of the analysis that is possible. However, there are many things that can be done. So yeah, these things also talk on the same topic. And okay, I am just skipping a few slides. So this slides also talks about why use R for network analysis, and specifically this iGraph and another package. I missed that writing. Okay, so that package called SAND, the Statistical Analysis of Network Data. In short, it is called SAND. It is actually, this package is compiled by the authors so that you all can, or we all can, refer to the examples as it is. So like reproducible examples. And this is the organization of the book. So the first two chapter talks about data manipulation, visualization, and numerical characterization. We will try to discuss up till this only in today's discussion. After that, there are mathematical statistical models for inference. And the last parts talk about dynamic processes, and they are modeling those kind of network flows and dynamic processes, which will eventually come up in the upcoming talks, hopefully. So yeah, this is all about how to install the packages and all. They also have a GitHub repository. I think all the codes are there. And also in the WhatsApp group, Pratik has requested for this Python version. So I also saw that this iGraph package has a Python iGraph version. So it is also there for Python implementation. So you can use that. Okay. Yeah. So okay. So now we move on to some real topics. So the first chapter, I would say it is the first chapter because this talks about something new, not just a synopsis. So manipulating network data, we will see how it is done. So what is a network? It is a network, or a graph simply is a collection of vertices and edges. And these graphs can be decorated as we have seen for that law graph, right? Lawyer's graph, that we can change defined attributes, vertices, edges. We can provide them some shape, some color, and change their size. So that are defined possibilities. And we will see how we can, what are undirected and directed graphs, different types of representations of any graph, and some operations of graph. Some of these topics may be familiar to some of you, but we are discussing this for the sake of completeness. So yes, what is a graph? A graph is written as V command, where V is a set of vertices and edges are like, it is a set of ordered or unordered pairs. So then now there is a subtle difference in ordered and unordered pairs. If they are unordered, that essentially means the order doesn't matter. So that is an undirected graph. So whether U maps to V or V maps to U, it doesn't matter. Just an edge exists. And that is relevant for many real life applications, whereas it is not relevant also for many of the other cases. There we use the directed graphs, where this edge set, so basically this set is an set consisting ordered pairs, right? So tail to head means like the first term is like the source and the other term is where it ends. So all these things can be generated, and I have written our codes chapter wise. I will share those codes in a GitHub repository. So yeah, don't worry. So in iGraph, we use these kind of functions are there to specify some toy examples. So these are some of the examples, like the first one is an undirected graph. I hope you all can see the graphs clearly, right? Or are they
Yes,
too small?
it's visible.
Okay, all right. So now these are the like three kinds of differences. The first one just has vertices and edges, and you can see the labels are just some numbers. So the numbers are from 1 to n, where n is the cardinality, the number of vertices. There is a very common practice in defining many graphs. You can just number them. However, not always it is relevant, like in the labeled graphs, that is Sam, Mary, and Tom. Okay, so these labeled graphs have names for each vertices, and the edges are directed. So these are arrows. So this gives more information sometimes than undirected graphs. Now we don't always see these pictures, right? Or we don't transfer from one person to another person. Like graphs are not transferred, the data is not transferred in forms of images. So how do we encapsulate the information, right? So there are three ways, three common practices. So I have taken this very simple graph, 4 vertices and 4 edges. So there are 3 possible representations. The adjacency list is like you write down all the vertices, and in bracket you write like A is connected with B and C, as you can see, B and C. And B is connected with 3 nodes. So this is like a list where each vertex, and in bracket we write down the vertices to which it is connected. The edge list is like you just write down all the edges. So there are 4 edges: AB, AC, BC, BD. So AB, AC, BC, and BD. So that is another way. And a mathematically popular, I mean, many of the mathematical operations that we will do for eventually is based on this adjacency graph, or sorry, adjacency matrix. What is an adjacency matrix? The I comma jth element is either 1 or 0, or it can be something different. So if it is 1, it means that the I comma jth pair is connected. So the ith node is connected with the j node. And as you can see, this is an undirected graph. So as a result, this is a symmetry matrix, right? But for a directed graph, the convention is that rows are considered as heads and columns are considered as tails. So I comma j will be 1 only if there's an edge from I to j. All right. So now there are some more operations that can be done. Some, not more operations, these are the first few operations that we are seeing. So suppose we have this base graph, and we can consider a subgraph. So what is a subgraph? Subgraph means that we have a subset of the vertex set and a subset of the edge set. And the complement means the vertex set is same as the original graph, but the edge set is complement. So where are we taking the complement? We are taking the complement from the set of all possible edges. So that is all sometimes called as the complete graph. So the set of all possible edges between a graph, you subtract these edges, you get the complement graph. So basically these are the edges that doesn't exist in the original graph. Okay. Again, yes, Pratik has any questions?
Yeah, so here I have
Yes.
this question, that just to make sure that I've understood this correctly. So in the base graph, I see 1 is connected to 2 and 3. So it
Yeah.
means in the complement, it will be connected to all those things apart from 2 and 3.
Yes. And that is the case. Right. Yeah. That is the case. So it is connected with 5, 6, 4, and 7. So yeah, that is one way to think that. And another way to think is that you consider that all possible edges, you just subtract the existing edge set from that possibility, and then you get this new edge set. So essentially, you are correct, absolutely correct. Yeah.
Yeah, okay. Yeah, just wanted to have that intuition. Thanks.
Yeah. Yes. So these are the 2 basic operations. Now, again, the subsection 2.3 talks about vertex and edge attributes. So this is like the same thing, colors, weights, and all. Okay, so moving ahead. Another important class of graphs is weighted graph. So weighted graphs mean that now the edges are not just saying you that they are connected, but they talk about something much more. They talk about how well they are connected, like in a Facebook network data. It can be very much of interest that how frequently two friends interact. So like I in my friend list have, I don't know how, some thousand of people. I don't interact with all of them. There are very few people with whom I have some interaction. So that really talks about our my social status and social relation with those people. That can be of great interest for like those data analysts, right? So this is just a simplistic representation. And here actually like this E of G dollar word, this is an R syntax. And I have those R codes. You will all will be able to see those there. So we can put the weights inside, okay, the it set. Instead of just having a 1 0 kind of this adjacency matrix, now we'll have some values, numerical values. And those values can be normalized, they can not be normalized. Like a very common type of weighted graph which is used in many statistical analysis is the distance graph. So where the weights are like the Euclidean distance. And many graph-based methods are based on this distance-based weighted graph. Okay. So now in the next section, we will cover this basic vocabularies properties to describe these notions. Yeah, so the difference between a simple graph and a multi-graph, there are some things called as multi-graphs, ideas of neighbor, degrees of vertex, okay, reachability, connectivity. I think you all can understand these things. Connectivity means that two nodes are kind of connected through edges. So you can traverse in that graph, you can start from one end and you can end up somewhere. Distances and traversals, yeah, talks about the same thing. Distance, however, there is an interesting notion of distance. We will come on to that. So, yes, Aishan has some question.
Yeah, sorry, I was not able to
Hmm.
ask this before.
Yeah, sure.
My question was regarding the complementation graph. Um, so we're basically trying to eliminate those edges which are not present, or we're trying to consider those edges which are in the complete graph but not in the original graph. So,
Yeah,
for instance, in a particular case where we are dealing with, in the first place, we are dealing with a graph having lots of edges. So it has a lot of connectivity involved. So for its
hmm.
complementation, then will it hold of much importance, or will it hold much information?
Actually, it will, I think it will be more informative in that situation. I mean, visually speaking. So if you just take the complement in a densely connected graph, it is very difficult to visually see all the connections. So it is more relevant to see what connections are not there, right?
Okay.
So in that way, maybe it can be. So you talked about this notion. I will search out. I'm not sure, but I'm just sharing my views on this. Okay, yeah. So that
All
can
right.
be of use in that way. All right. Okay, so these are some notions. So simple multi-graph and weighted graph. Okay, so weighted graph has already been explained. Multi-graph is something interesting, like they are not directed, but here two edges can have multiple connections. So in the sense that if they are weighted, there are two edges, and those two edges correspond to two different attributes and their different weights. So in fact, one of my seniors in ISI is doing a research on hypergraphs. So I'm not talking about hypergraphs, but just for all of your curiosity, these are like generalizations of graphs itself. So there the concept of edge is not here. The concept is limited to edge, right? So limited to edge in the sense edge can connect only two vertices, two nodes. But in hypergraph, there are generalized edges which can connect more than two graphs, or there are more complicated structures which are building blocks, and that leads to more, I mean, more deeper understanding of some structures, physical structures. Those are very complicated, very new to literature. Yeah, Pratik.
Yeah, so just to ensure that I've got the intuition of hypergraphs correct,
Yeah.
so it's more generalized than the graphs we are studying here. And one way to, and obviously we may not be able to visualize what I'm about to say. It's like we see this edge between 1 and 3 in multigraph.
Hmm.
So in a hypergraph, it can be something like that the edge is connecting 3 vertices simultaneously.
Yeah, exactly.
Okay.
Exactly. Right. So
Thank you.
it's difficult to visualize hypergraphs. Maybe in the end of this series we can talk about some of those things. Yeah. Okay. So having said that, the adjacency and neighbor. So the adjacent nodes of any particular node are like those who are directly connected. Okay. And this 5 has these 3 neighbors. And the degree is like the cardinality of neighbor. So it has a 3 degree. So these degrees also talk a lot about like how important a particular node may be. Yeah, so now this essentially talks about the degrees. This graph actually, I made this graph in such a manner that the sizes are proportional to degree, even though they might look very same. But if you see carefully, this 1 and this 7, they are smallest. This 4 is kind of the largest one because it has the highest degree. So in a huge graph, this vertex sizes, if you change them with respect to degrees, then that can give you more information sometimes. Yes, now in directed graphs again, the concept of degree generalizes. So now it measures like how many edges go out of of a node and how many comes in that node. So that is kind of the in degree and out degree, right? So this is now a pair of degrees, and this is the generalization for directed graphs. Again, components, these are like very interesting, and I think some of you who are familiar with clustering literature may have seen something called as spectral clustering, right? So the spectral clustering actually utilizes this graph-based structure, and it tries to find out components, whereas where the graph is the weighted graph. If you remember, you consider the distance graph, right? Or if not the distance graph, some sort of Laplacian graph, which is connected with the distance graph. But those things will be covered in the clustering chapter. But yeah, so these are like the clusters. So these are like components. Components means two components don't share any edges, and each component can be called as a cluster. Okay, weakly connected and strongly connected notions are there. So for undirected graphs, if the graph is connected, that means you start from any vertex, you can end up in any other vertex through a traversal, means undirected graph. So they are sort of connected. Any two edges are connected through some path, not necessarily directly. If they're directly connected, that is a complete graph. So that talks about weak connectivity. Strong connectivity is directed. For directed graphs, you have this directed walk, and you can end up from one edge to the another through a directed walk. And that should be true for all possible pairs of vertices and nodes or nodes. But like we can see, this is an connected graph. It is weakly connected, but I think it is not strongly connected because you can't uh, go from Mary to Sam through a directed traversal. Only these two are connected. So this is a simple example of such a case. Yes, exactly. This is written that weak is true and strong is false. So this is one such example. Okay, now this is an important, I find it a very interesting and important concept. So it talks about distance. So how to define distances or diameter? If you all think about this descriptive statistics, there we learn about range, right? Range of a data set. So diameter is kind of the range, and distance is the Euclidean distance in RD or real line. But how to define distance here? So the notion is, I think I can show the mathematics also. Yeah. So the geodesic distance is essentially the length of the shortest path between two vertices. So you will calculate the distance between two nodes, right? So if you see this node and this node, so you can go from 5, 4 to 1. So this is like you have to cross two nodes, kind of, right? And the path is like 1, 2, 3. So you have to cross three paths or three edges. However, you can go this direction also. That is 5 to 3 to 1. Here you have to cross two edges. So this is the shortest, right? You can't find any shorter path. So the distance essentially here is 2 because this is a unweighted. This is just a undirected graph with 1, 0 binary weights. And the diameter, so it is the largest shortest distance. Basically, that's why the diameter is defined as maximum over all UV, where we consider the distance between U and V. So it is like the pair of nodes which can be non-unique, whose shortest path length is largest. So here like 1 to 6, so here we connect again 3. So essentially the diameter is, you can say it is equal to 3. So was that clear or should I explain it again?
Yeah, it was clear.
Yeah, okay. So diameter tells us that the furthest apart, how further apart any two vertices are in terms of shortest paths. Okay. Yeah, now these are like, this is a cycle, a closed path with all vertices. These are some of the examples. I forgot to mention other two kinds of graphs here, but okay, I'm skipping this slide for the time being. Anyways, but this is important. In acyclic graphs, what is a cyclic graph and acyclic graph? So you all can understand, for an undirected graph, cycle means basically you can go in an infinite loop. So there is a set A, B, C, D, and all the edges are there. So you can go from D to A, you can go from B to C. So there is a cycle, and the cycle is a set of edge, basically a set of edge such that this kind of structures are formed. And directed acyclic graph. Okay, acyclic graph, first of all, what does it mean? It means that no such cycles exist. Here we can see one such cycle exists. But directed acyclic graphs, that is in short called as DAGs, they have they shouldn't have any directed cycles. So here we can see no directed cycles are there. And quite mystically, the book mentions that these DAGs are of good interest in graph theory and network analysis. However, I have not seen those things yet, but I'm interested and keen to know how these are important in those kinds of analysis. Okay, so with that we conclude this chapter and we move on to the third one. This talks entirely about visualizing networks. Yes, any questions? Yeah, Pratik.
Yeah, so here I wanted to understand cyclicity a little better. So the definition is saying closed path where all intermediate vertices are distant. So I can intuitively see that A, B, C, D are closed. As in
the letter E cannot access that thing. But can there be something closed path, but intermediate vertices are not distinct? So, what would it be like?
Okay, so that can happen, I think, in case of multigraphs. So in multigraph, if you just go back, just yeah, I just plot. So you can consider a cycle like this, that 5 goes back to 4, then 4, 6. Right. So that is a cycle where 5 comes twice, or this kind of pathological situations may arise in case of multigraphs. So that may be a counterexample. Okay. Does that answer?
Yeah, thanks.
Yeah. So we move on to the next chapter. I would now ask the hosts. So when did I start exactly, and by what time I should end? I don't want to extend it too much, otherwise it will be boring and hectic. I think I started around 6:40, right? So sorry, 5:40. Yeah. So I will go till 6:40. Okay. Yeah. Okay. Thanks, Avradita. So I don't know whether I will need to finish, but anyway. So the third chapter devotes on the topic of visualizing. So yeah, these are important. These are quite important things. Like it combines mathematics, aesthetics, and algorithms in the sense that visualizing a graph is very important thing, because just like visualization in descriptive statistics is a very important part. So different types of descriptive diagrams, they talk many things about those kind of data sets. They reveal many patterns, and that makes the inferential analysis simpler. In that same way, forming networks properly actually churns out very useful information. So here in mathematics, by mathematics, it talks about graph structure, and we will see some algorithms are there which actually helps in creating those graph structures. So yeah, so what is a good choice of layout? It should reduce visual clutter, that it should have fewer edge crossings. So what are edge crossings like? If you think about many edges and the many vertices and the edges, there will be crossings amongst edges, and it often creates a problem to visually understand which are the connected nodes. So the drawing is not just decoration, it is a key part of interpreting the network. And the network is not in that way a very rigid kind of structure. You can place vertices anywhere, and you can also draw edges like in any direction. So plotting the vertices in the right position and drawing the edges in the right direction is important. So one such layout are the graph layouts, like the circular layout. So the circular layout is, this you might have seen in some places, like I think in some pages, these are used to show collaborations between authors of research papers. So how is this useful? Okay, so the circular representation is useful to understand, like for each of these nodes, you can understand essentially what is their degree, which vertices they are connected. But again, if you don't order them properly, this kind of a clutter can be created. So in the ordering, in the circular ordering is very important, and that is often done using some heuristics, like you consider whether there are some groups amongst them. So if there are groups, so you put them together, then another group, then another group. So in that way you can make the plots. Okay. And similarly, there is this lattice graph. I not don't exactly understand what this is, but whatever I read, it says that this is actually a 3D representation. So these are actually relevant in chemistry. The solid state crystal structures are like this. but it is very much, I mean, confusing, and it is also hallucinating to me to some extent. And this is a very interesting type of graph. It is actually attraction repulsion graph, and to be honest, I think this is called as FR diagrams. So this Prachterman, Reingold, I don't know exactly, I can't pronounce the names, but they gave some algorithm. The algorithm is motivated by repulsion of particles. So you can think this as a bulk of particles, and the distance between them is like the optimal distance where this system of particles will settle down. So exactly, I don't know the algorithm, neither do the book mentions about the algorithm. If on public demand, I can read and present that if you all are interested. So yeah, but the circular layout, so these are like the pros and cons. The vertices are placed evenly on a circle circumference. The preservers that preserves equal spacing. It is good for highlighting and connectivity patterns. Ordering of vertices around the circle affects clarity, so that's important. And this FR diagram, this is physics inspired. Vertices repel like charged particles, edges act as springs. Okay. Yeah, now I think it's more relatable, right? So the springs don't allow them to go away too much, whereas the repulsion don't want them to be too close. So there is a optimal kind of solution. But I was reading a Wikipedia article. It says that these algorithms are run in order of n cube. So if n is the total vertex number, that is order n cube. It is quite hectic, I mean heavy, resource heavy. So some greedy solutions are proposed, and I think one of them will be covered by us. Yeah. So in the R syntax, these are very simple. These two functions are there in this iGraph package. It makes life very simple. Layout with F and layout in circle. So yeah. So now having said that, we move on to the next subsection, that is decorating graph layouts. Now why decorate? So for that, two data sets are given. These two data sets, I think, are analyzed subsequently in many places in this book. So it talks about the first data set is Zachary's Karate Club data set. And there is an interesting event that happened here, is that it is like a social network of 34 members in a university karate club. But these friendship ties were observed over a period of 2 years. And in between, some conflicts happened. So between the admin and instructor. And as a result, the entire group was split into two. Okay. So this, we will see the graph structure. And in iGraph, this is given as an inbuilt data set. And this classical lawyers data set, it is consisting of 71 lawyers. And it has like multiple relationships. We have already discussed about this. So yeah, so this is like the plain representation with the decorated representation of this first data set, the Karate Club data set. And here you can understand the difference. So size is given by, I think, strain, some sort of I'm forgetting exactly how they determine the size. Perhaps the experience, a number of years of this black belt, blue belt kind of things. And these are like the two heads of these two groups. There are some red edges, some blue edges, and some yellow edges. Those yellow edges are connections between two groups. So for some, information passing. So yeah, this is how exactly the graph was given in that book. And yeah, this is again that lawyer's data set. It comes up again in this chapter, in this section. So I mentioned it here again. The previous one was a snapshot, and this is, I think I wrote the code for this. Yeah. So you will find out all these codes according to the section number. I will share those files. Now, an important problem is visualizing large networks. So you can use those attraction repulsion algorithms, and there are like these true algorithms the KK layout, two layouts based on two algorithms, and the DRL layout, distributed recursive layout. So again, these are like, they don't mention the algorithms, but they are based on the philosophy. The first one is based on the philosophy of this force-directed method. The second one is like multi-level force-directed algorithm. So it is a greedy solution. Whatever I read, it says that it is a greedy solution of this algorithm by KK and this FR graph. So these are the representations of, I think I forgot which dataset I used for that, but this is how they give the layout as. So yeah, you all can experiment with these things and we can go deep on these topics. However, these are very technical, like the algorithms. These are a class of algorithms, layout, optimal layout selection, class of algorithms, and force-directed methods. So defined algorithms are proposed in the literature. Okay, now another way to simplify or to visualize large graphs is to simplify them. So the simplification can be thought of as in descriptive analysis, descriptive statistics, we do this binning, right? So we consider bins of different widths, and there we have this we summarize through the frequency. Similarly, this coarsening or grouping is there, where you take some similar nodes, you consider that as a big or bigger node, right? And using that, you come to some conclusions about the structure of the network. And egocentric view means you focus on one particular node and its neighborhood, like zooming into the graph. So this is an example of coarsening graphs. So you combine blocks into party. These are like meta nodes, so collection of nodes. And thicker edges means more cross-party links. So the edge widths can be determined if there are more interactions between these two groups. And there will be an edge. An edge will exist if and only if there is an edge between those two groups, right? So you are combining them. Similarly, for this karate dataset, this is the egocentric view for the first individual, for the 34th individual. So this is another way. However, that karate data was quite small, but this is a toy example to motivate. So okay, till now we covered about 3.5. We can move on to descriptive analysis if you all are interested, or we can stop here. So what should I do?
I think all of this is so awesome that our digestive capabilities are not enough to. No, I'm not joking. I'm not joking. I'm telling the
Similarly for me also.
Yeah. So
Yeah.
I think we can pause over here and
Yes. That
give
will
us
take
time
as
to
well.
digest.
Sure, because this fourth chapter, actually I've just written the contents, but I have not prepared the entire content. It is just there till vertex centrality. So I mean I will finish this chapter and it will be best to present it in the next session. So yes, I think we can conclude it here. So thanks to all of you. And before ending, any questions, queries, or comments? Okay, yeah. Thank you, Supratim. Thank you, all the participants.
Yeah, I have a question on the distance, which was quite intuitive, honestly. The geodesic distance,
Yeah.
which was the shortest path.
Mm-hmm.
My question is, later in the book, or do you personally know of a distance which is the longest path, but each node is touched only once? So, like to give an example, I'm going from my school to my home. There is a shortest path, Suppose there are 5 locations in between, I can take a shortest path which covers only 2 locations. But I deliberately want to hang out with my friends, so I go in a path where I can cover the maximum locations and then reach my home. But I will not go to one location twice. So I'm assuming such distances should also have a kind of utility in modeling.
Yes, I think it has. Like, I don't cover this centrality. Just I'm giving my comments on this. So the centrality essentially talks about how centered a particular node is. Okay. So there we use this distance, the notion of this geodesic distance. And there they have defined it in the way that if a node has low distance with most of the neighboring nodes, or if you add up its distance with all the nodes, if that is small, that means its centrality parameter is high. Okay, in the sense that it is located in the middle. So it has less distance to all the neighboring distances. Now, what you said, that can directly give a notion of centrality perhaps, in the sense that if the longest distance from a node to all the neighboring nodes are small, then it is also in the center. So if your house is in like center of Kolkata, whatever longer path you choose to say go somewhere, that will be kind of small, not that big. The longest part will be smaller. So your home or the location where you start is kind of in the center. So for defining those centrality parameters, I think we can use that. And there will be many such applications. I myself, to be honest, I don't know 90% of the literature. I'm learning. And it is really a great that opportunity that StatsUP has given me to learn. So thanks to all of you for giving me this opportunity. Yeah. Any other queries or comments? And by the way, does that answer, Pratik, your question?
Yeah, it opens a
Answer.
whole
Hmm.
chain of discussion. I think that is the purpose. So recently, I came across an instructor who said this very beautiful line: "I'm not here to teach you; I'm here to make you think." So
Exactly.
that
Oh, I just forgot to just show this slide. So these are the packages, Python iGraph, network X. These are whole lots of, I would say, much more than R. Okay, these packages exist. Okay, I will share this slide. Uh, I'm thinking whether to share now or after completion. Anyways, I am sharing the codes and all. I will share this page to you personally or in the group. Okay then. So I am stopping the recording.